Hey everybody, welcome back. Here we are, Unit 3, Lesson 3, Survivorship Curves. And without further ado, let me get rocking and rolling through this one. It is going to be a little short one, but it's actually a pretty cool one. I actually really like the idea of survivorship curves, or the concept of survivorship curves. It really talks about something that is very applicable, and at the very end, we're going to kind of tie it all together with human survivorship curves. And you guys are going to have a little activity based on this. But what I really want you to understand is how this applies to ecology, and then why are we learning about this now. So let's talk about what does the College Board want you to know. They want you to be able to explain survivorship curves. That's simple. Boom. Explain what this topic is. But again, it's not just a very shallow concept. It's in-depth. They want you to be able to know what you're talking about. So let's talk about what is a survivorship curve so we can get this lesson over with faster. It's a visual representation. It's a graph. Survivorship curves are a graph. There you go. Boom. Done. And it's the likelihood of a survival of a species as they mature. So what we're really looking at is how likely are you to survive year 1, year 2, year 3, up to whatever. Now, the thing is, it's normalized. So utilizing logarithmics, we normalize it because humans, average life expectancy of a human, somewhere between 70 to 90 years old, depending on who you are, your background, all sorts of other things like that. Compare that to a small little mouse, like a field mouse. Field mice aren't expected to live to be 70 or 80. They might only be expected to live to 3 to 5 years. Most birds are only expected to live, especially the small songbirds, 3 to 5 years. Although we do have rare occasions where you have bird banders that are like this same bird has showed up to the same habitat for 12, 13 straight years, which is unheard of in most individuals. But it's normalized. So, yes, mice might only live to be 5 years old, and humans might live to be 80 some years old, but the same percentage of the time frame at the bottom there will help us to, or over time, will help us to determine which survivorship curve these different individuals fall into. Now, there's 3 different types, and they're very creatively named. Type 1, Type 2, Type 3. Here's the thing. I hate Type 1, Type 2, Type 3. That doesn't help you if you forget which side is the 1 and which side is the 3. The 2 you're always going to remember. What I want you to be able to do is more describe what is actually happening than just saying, oh, that's a Type 1 curve. So I really want you to be able to describe what's happening. So let me at least go through and define the different curves for you here. Again, there are 3 different types. Type 1 is an individual that has a very high success rate from birth to maturity, and then as they get older, at the end of their expected lifespan, they start to die off. So they're going to have a very high success rate or a high survival rate, and then as they get to their end of their lifespan, you'll see their survival rate will start to drop. There are other organisms, type 2, which have an equal chance of death at any point in time in their life. They're usually prey species. And the way we think about this, or the way I think about it, is type 1 is a perfect example of humans. We raise our young, and for the most part, you're expected to live to your full lifetime. Does that always happen? No, unfortunately not. Okay, but for the most part, as we average all the data, which you guys are going to do in a little lab, as you average all the data, you will see that we do actually kind of fall into this pattern. How about type 2? Well, type 2, I think of things like rabbits, squirrels, small songbirds. There are predators that are out eating them every single day. Squirrels are some of the dumbest animals on the planet. They run full speed into traffic. All right. It doesn't matter if you're a very young squirrel or a very old squirrel. You still run in traffic, you still die. There's still hawks that pick them off. There's still foxes that pick them off. So there's a lot of other predators that are constantly after them. I can't really imagine what life would be if you had to constantly live in fear of being killed by something from above or from the ground, but they do. Lastly is type 3 individuals. Type 3 individuals means that you actually stand a very high chance of dying very early on in your life. But if you can survive that first year, or you survive that first little stretch of dangerousness, once you hit maturity, have a great chance of living out your entire life all the way to the end. Think of trees, for example, maple trees. They will drop thousands of samara, the little helicopter things. As those samara all spread around, most of them will not grow into a full tree. That is offspring from that maple tree, though. Those are fertilized seeds. They're ready to go. Most of them will not grow. But if some of them do get in the ground, some of them do grow, once they get past probably that first year, they're probably going to live to be a couple hundred years old as long as chainsaws don't come around. The one thing about all of this, it does not factor in human destruction of the organism. What we're really looking at is just how do these organisms naturally exist in their natural ecosystem. Oysters, for example, when we look back at that K versus R strategy species, oysters will have something like 500,000 offspring at a time. 500,000 at a time. And then if only 1% of them survive, that's still an immense amount. Right? 1% is 5,000. So they're probably actually looking at maybe 5 offspring will survive from one oyster producing, which is an incredibly low survival percentage. But once they are established, they will be perfectly fine for a long period of time. So let's go and take a look at these graphs. So here's the graph. Look at 1, 2, and 3. And let me kind of go through and describe this for you so that you kind of understand. Over here on the y-axis, you will see the number of survivors as a log scale. So this is saying at the top, 1,000 would be perfect survival, every single individual. Okay, and then at the bottom would be like barely one survives, right? Like very small amount. Now, if you look at type 1, you see it stays very high because we invest a lot of energy in our offspring. All right, it's never going to decrease or it's never going to increase over time. But what it will do is it will decrease over time, right? Because organisms are going to die off. Then they reach this, maturity or this near the end of their lifespan, and you start to see the things start to drop. Sorry, I seem to have lost my camera connection, so I kind of come back here. I'm sorry for the quick pause in there. Caught me off guard. But that type 1 is humans. Right? We spend a lot of energy into our offspring, and then as you get older, you die off. Type 2 is the middle line here. Okay, and in that middle line, you see that there's just an equal chance of death, constant rate the whole way down. And then finally, your type 3 is where if they survive this first time period, they survive to the end of that first time period, they will live out to their maximum life pretty safely. But it's that first time interval they have to survive. Think of sea turtles. If they make it to the water, that's great. Most sea turtles die on the beach. Most trees aren't going to make it. Now, again, humans usually are mowing them down, but it's just too much competition for things. Or acorns, for example. Oak tree producing all those acorns, well, a lot of them are food for blue jays or squirrels or various other things like that. So there's a lot of competition for those foods or those offspring of type 3 type reproductive strategy. Now, the thing is, this is not always perfect. All right, that type 1, type 2, type 3, those are perfect designed graphs for you to understand. What we actually see is something more like this. The idea that different organisms, if you plot their number of survivors over their maximum lifespan, the time intervals, you can kind of see how different organisms have changed. Right? There's not always a true 1, 2, or 3, but you can kind of see based on the different types of organisms where they fall. Now, elephants are a very interesting one that's going to fall in here because they take a long time to reach full maturity. And once they do, then they're kind of safe. But you see that they are kind of almost like a prey species during certain times of their life. Now, how does R selected and K selected factor into this? Again, we talked about that in the previous lesson. We are looking at the amount of energy invested into your offspring and the rate at which you produce offspring. Remember, that's the major difference between R and K selected. R selected species don't spend a lot of energy on their offspring and they reproduce very rapidly. Why? Because they're oftentimes going to die off faster. So usually our selected species are what we would call our type 3 survivorship curve. Humans, examples of K-selected species, we exist up at the carrying capacity and then eventually die off because we spend so much energy raising our young. You think about your parents, they've invested a lot of energy and time and focused their efforts on raising you to reach your adulthood. So please don't screw it up. All right. Finally, let's apply this to human survivorship curves. And this is what you guys are going to do in a little lab, but we're going to look at data from cemeteries about human survivorship and how it's changed. And if you look at these graphs, what you see is like from 1900 to 1980, the curve part of the survivorship curve for humans has changed. Now, what has actually happened is it's gone from this almost like a type 2 curve to a very, very traditional type 3 curve. Now, why is that? Well, it's not because we have different predators. It's not because we have different prey. What is it? What is causing this human curve to change? I'm sure most of you can answer it. And a lot of it is the way our society has developed. We've developed medicine. We've developed cleaner standards of living. And because of it, our life expectancy is increasing. We've eradicated a lot of our diseases and illnesses that would normally wipe out children or people at any age. Now we have people living to adulthood. It's expected. If you can make it past probably first 5 years of life, you're probably going to live to your maximum lifespan as long as you don't have any outside or extenuating circumstances dealing with it. All right. So, do you understand survivorship curves? Do you understand that there's different types of survivorship curves on the planet? There are 3 different ones. Now, if you can compare type 1, type 2, type 3, or if I just kind of got rid of the numbers and called them A, B, C, could you compare A, B, and C? If you can, and if you know the differences between type 1, type 3, or type A and type C, or whatever, and you can understand how those organisms are different, fantastic. You're doing great. If not, get a hold of me, and I'll make sure we spend some time going over those topics. Thanks for tuning in today, guys. I look forward to seeing you with the next lesson. And in the meantime, have a great day.
You like that lesson? I know you did. So why don't you go ahead and smash that like button right now. Go ahead and comment. Tell all your friends about how great that lesson was. And make sure you subscribe, because I'm going to keep bringing you AP environmental content that you're going to want to watch. Or do whatever else those other YouTube channels tell you to do. And with that, Maloney, out.